Hi everyone. So today we're going to sort of wrap up some of our electrochemistry discussion. We'll have one more lecture that's sort of optional. It will be about different types of batteries. We'll talk about fuel cells, so we'll apply everything we've learned to real-world electrochemistry. So in this lecture, we're going to wrap up some of the calculation stuff. All right, so last time we had discussed the equation where delta G for a reaction under standard conditions is equal to negative N times Faraday's constant times E cell, so the cell potential. Now, we also know that delta G is equal to negative RT times the natural log of K. So what if we replace delta G with negative NF E cell? Then we can set that equal to negative RT times the natural log of K. And if we rearrange the equation, we can solve for E cell. So we can say that the cell potential is also equal to RT over NF times the natural log of K. Or we could also solve for K, we could solve for T. It just depends on what we're trying to determine. Now we could further simplify this equation because we already know the gas constant. And if we're under standard conditions, we know that the temperature is 298 Kelvin. We also know Faraday's constant. So plugging those in, we get this more simplified equation where the cell potential is equal to 0.0592 volts over the number of moles of electrons times the log of K. All right. Now, there isn't really a derivation for this equation in your textbook. Well, there sort of is, but basically that natural log that we saw earlier is converted to a log. So if you want to learn more about that, let's see, I think it's on page 908 of your textbook. So if you're curious about where that equation comes from. All right, so we're going to use this equation, and let's go over an example. We're going to use the tabulated electrode potentials to calculate the equilibrium constant K for the oxidation of copper by hydrogen at 25 degrees Celsius. All right, so we've got an equation here where copper is reacting with two hydrogen ions to produce copper ions and hydrogen gas. All right, and we just saw that we can calculate E cell by setting that equal to 0.0592 volts over the number of electrons that are transferred in a reaction times the logarithm of the equilibrium constant K. All right, so eventually we'll rearrange this equation to solve for K. So if we're solving for K, then we need to determine all of the other variables. So we need to find E cell, and we also need to determine the number of electrons that are transferred for this equation. Okay, so let's write out our half reactions. So first, let's determine the oxidation numbers for each of our reactants and products. Okay, so copper initially is pure. It's in its elemental form. So that has an oxidation number of 0. Hydrogen ions have an oxidation number of +1. Our copper ions have a charge of 2+, so our oxidation number is +2. And hydrogen gas has an oxidation number of 0. So copper, it looks like, is losing electrons. So that's oxidation. And then hydrogen is gaining electrons. So that's reduction. Okay, so if we write out our oxidation and reduction reactions here. Sorry, I was looking for my notes. So the oxidation half reaction is for copper. And the reduction half reaction is for hydrogen. So we've seen these before. And when copper loses electrons to become a 2+ ion, it loses 2 electrons. And when hydrogen is reduced, or when hydrogen ions are reduced, they gain 2 electrons. So luckily for us, the electrons balance out. So that means that N will equal 2 because 2 electrons are transferred. All right, so we found N. So I'll just write in red up here. N is equal to 2 moles of electrons. So now let's determine what E cell is. I'll do that in blue. So let's look up the potential values for these half reactions. So for copper turning into copper 2+, you should find that the potential value is 0.34 volts. And for the reduction half reaction, that's our standard hydrogen electrode. So remember, that always has a potential of 0. Okay, so when we calculate the cell potential, remember we take the potential for the cathode and subtract the potential for the anode. So which half reaction corresponds with the cathode? Oxidation or reduction? Reduction, right? That's the cathode. And that means that oxidation is the anode. Okay, so we're going to take the value for the cathode, which is 0, and subtract 0.34 volts. So we get negative 0.34 volts for our cell potential. So we'll just write that up above. Oh, if my pen will let me. Apparently it wants to write in bold today. Okay, so that's equal to negative 0.34 volts. All right, so now we have all the values we need to solve for K. So on the next slide, we'll solve for K. All right, so again, our equation is 0.0592 volts over N times the logarithm of K. And we know what E cell is. We just said it was negative 0.34 volts. We also determined that N is equal to 2 moles of electrons. And then we have the log of K. So let's rearrange this equation. So let's just solve for the log of K initially. So we'll figure out what the log of K is, and then we'll take the inverse logarithm. Okay, so the log of K will equal negative 0.34 volts times 2 moles of electrons over 0.0592 volts. Okay, so if we plug that into our calculators, we should get a value of negative 11.5. Let's see. And actually, that will be unitless. So volts do cancel and we're left with moles of electrons, but since we're calculating an equilibrium constant, remember that those are unitless, so we won't really worry about units here. Okay, so let's take the inverse log of both sides. So K will equal 10 to the negative 11.5. And then that will equal 3.3 times 10 to the negative 12. Okay, so if we're looking at that value of K, that's pretty small. So that's a lot lower than 1. Excuse me. It's a Friday. My brain is going. Okay, so if we look back up at our value for E cell, it's negative. It's negative 0.34 volts. So if E cell is negative, is this reaction spontaneous or non-spontaneous? It's non-spontaneous. So we would expect K to be quite small. Additionally, if we look at the E cell values here, so the, or not E cell, but the potentials for the half reactions, notice that the value of E for copper's reduction here, or oxidation, excuse me, is 0.34 volts. And that's quite positive. And remember, when our E values are positive, those half reactions prefer to be reduced. So copper actually doesn't want to be oxidized. It wants to be reduced. So the forward direction here for this reaction is non-spontaneous. So there's a lot of different ways that we can kind of analyze these processes and figure out if they're spontaneous or non-spontaneous, but we should always verify our answers to make sure that they follow what we know conceptually as well. So we're gonna train ourselves to think like scientists. For me, that took a lot of years, so don't feel bad if it's all new to you right now. Okay, so now that we know how to use that equation, where E cell is equal to 0.0592 over n times the log of K, we're going to expand on that idea. So remember in chapter 18, we learned how to calculate everything under standard conditions, and then we learned how to calculate Gibbs free energy under non-standard conditions. So let's learn how to calculate a cell potential under non-standard conditions. Now remember that from our previous discussion of Gibbs free energy, we saw that delta G under non-standard conditions is equal to delta G under standard conditions plus RT times the natural log of Q. And remember, Q is our reaction quotient, where we have products over reactants. And that can be in concentration units or in pressure units. Now, remember, we also said delta G is equal to negative N times F times E cell. So we're just going to replace those delta G's with that expression. And notice too that we are missing that little degree symbol on the left because those are under non-standard conditions. All right, so now if we rearrange this equation, so if we divide both sides by negative NF, we get that E cell, so the cell potential under non-standard conditions, is equal to the potential under standard conditions minus RT over NF times the natural log, or natural log of Q. And remember, we can just plug in what R is, what T is, what F is under standard conditions, and that will give us this equation here. All right, so this looks very similar to the last equation that we used. However, this time we're calculating the cell potential under non-standard conditions. So this equation is called the Nernst equation. So this is going to be used to determine the cell potential of an electrochemical cell at non-standard conditions. Now, this can be useful in a lot of different scenarios. So, for instance, what if we want to create an electrochemical cell where we're using copper on both sides? So maybe that's all we have available to us. So on the left-hand side, you'll notice we have copper on both sides, and the concentrations of the solutions that they're in are both 1 molar in copper ions. Okay, so nothing's going to happen there because we have 2 of the same metals, 2 of the same solutions with the same concentrations. Electrons are not going to want to flow from one direction to the other. However, what we can do to promote the flow of electrons is change the concentrations of those solutions. So what if on one side, the left side, we have a lower concentration of copper ions, so 0.01 moles per liter, and on the right side, we have a higher concentration of copper ions, let's say 2 molar. So what's interesting is electrons will want to naturally flow from the left to the right. Because we have such a high concentration of copper 2+ on the right, they can interact with electrons to form solid copper. And then on the left-hand side, copper can turn into more copper 2+. And it will give up electrons to do so. So electrons are going to flow from left to right. So we can use concentration and the same exact electrodes to create a cell. So this is called a concentration cell. Now, you could also do this with different electrodes and different ions. So you could, let's say, have iron on one side and copper on the other, and you could manipulate the concentrations to try to encourage more electron flow as well. So that's also a possibility. Okay. Now, if we're thinking about the Nernst equation, oh, actually, I don't want that degree symbol there. So in the Nernst equation, remember we have that logarithm of Q, the reaction quotient. So remember, Q is perfect for scenarios where we don't have an equilibrium constant, so we're at a different state in the reaction. We're not at equilibrium. So if Q is just equal to 1, which means the concentration of the products equals the concentration of the reactants, then this whole thing cancels out. It just becomes 0. So that equals 0 if Q equals 1. However, if we change the concentrations, then Q will have a value, and we can figure out what E cell is under non-standard conditions. All right, so just as a summary for concentration cells, it is possible to have a spontaneous reaction if your oxidation and reduction reactions are the same, as long as the electrolyte concentrations are different. So that's the key part there. And calculating the cell potential using the Nernst equation will help us determine the direction of spontaneity in the cell. So electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution, just like we saw on the last slide. So on the left-hand side, we had oxidation, and that was the less concentrated solution. So when the copper electrode oxidizes, it's going to produce more ions. So we're going to see an increase in the ion concentration in the solution. And then on the right-hand side, we had reduction of the solution ions. So they were gaining the electrons and turning into pure copper. So we're actually going to see a decrease in the ion concentration as the reaction proceeds. All right, so hopefully that makes sense. So let's go over an example. Now, in this example, we don't have the same metal on each side. We're going to have two different half reactions, but the concentrations will be different on each side. So we're going to have to take that into account when we're calculating the cell potential. And we are under non-standard conditions because, remember, under standard conditions, everything would be 1 molar. But in this case, we'll find that the concentrations are different. Okay, so let's determine the cell potential for an electrochemical cell based on the following two half reactions. So we're already told that we have an oxidation half reaction where copper becomes copper 2+, and we lose 2 electrons. We're also told that that solution of copper has a concentration of 0.01 moles per liter. So I'm actually going to write below what that concentration is because it might help us keep track. Okay, so that's our concentration. And then we're told that the reduction half reaction, we have permanganate plus 4 hydrogen ions plus 3 electrons, and that's going to produce manganese dioxide, or manganese 4 oxide, and 2 water molecules. And then we're also told that permanganate has a concentration of 2 moles per liter, and then the hydrogen ions have a concentration of 1 mole per liter. Okay. So what we probably need to do first, let's actually write out the Nernst equation just so we can see which factors we need. Okay, so it looks like we need to figure out what E cell is under standard conditions. We also need to figure out how many electrons are transferred, and we also need to figure out our reaction quotient Q. So maybe what we'll do first is try to figure out how many electrons are transferred. So that means we need to balance our chemical equations. All right, so let's do that. So I'm going to rewrite the half reactions. Luckily, they've already told us how many electrons are gained and lost for each half reaction, so we don't have to go through all of those steps. Okay, so it looks like in the oxidation half reaction, there are 2 electrons that are lost, and in the reduction half reaction, there are 3 electrons that are gained. So those don't equal each other, so we'll need to multiply. Let's see, so it looks like we have to multiply the first reaction by 3 and the second reaction by 2. and that will give us 6 electrons for both. Okay, so I'll try to squeeze that in down here. So 3 coppers become 3 copper ions plus 6 electrons. And we have 2 permanganate ions plus 8 hydrogen ions plus 6 electrons. And we end up with 2 manganese 4 oxide molecules and 4 water molecules. Okay, so that's what we need to balance. So our electrons will cancel, and then what we're left with is 3 copper, which is a solid. We also have on the left side of the arrows 2 permanganate ions, which will be aqueous. We also have 8 hydrogen ions, which will be aqueous. And then on the right-hand side, we have 3 copper ions, which will be aqueous. 2 manganese 4 oxide molecules, which will be a solid. And 4 water molecules, which will be a liquid. Ooh, that's a long equation. I barely fit that on the screen there. Okay, so now that we have our balanced reaction, we know that there are 6 electrons being transferred, and we also can write out our reaction quotient using what we know about the products and the reactants. So we kind of killed 2 birds with 1 stone there. Okay. So now let's solve for Q. So remember, Q is going to equal the concentration of the products over the concentration of the reactants. So looking back at our products on the last slide, we have 3 copper 2+ ions that are aqueous, 2 manganese 4 oxide molecules, but those are solid, so we're not going to include those. And then we have 4 water molecules, which are liquid, so we're not going to include those either, because remember, in reaction quotients or equilibrium constant expressions, we don't include pure solids or liquids. So the only product there is our copper ion, but if we look back, we have a 3 coefficient in front of copper. So we need to raise this concentration to the 3rd. And now let's go back and look at our reactants. So we have 3 copper atoms, but those are a solid, so we won't include those. And then we have 2 permanganate ions, which are aqueous. So let's write those out. And that will be squared because there were 2 of those. And then we also have 8 hydrogen ions, which are aqueous. So let's include those as well. Ooh, we have to raise that to the 8th. That'll be interesting. All right, so now let's plug in the concentrations for each. And those are up above, or you might have already written them down in your notes. So for copper, we have 0.010 moles per liter. We're going to cube that. And then permanganate, we have a concentration of 2 moles per liter, and we're squaring that. Ooh, and luckily the concentration of hydrogen ions is just 1. So when we raise that to the 8th, that'll just be 1. So we got lucky with that. Okay. So Q, if we calculate this, should end up around 2.5 times 10 to the -7th. And again, this is unitless, so don't worry about units for this. Okay, so we know the number of electrons was 6, we now know what Q is equal to. The last thing we need to find is E cell. So looking at our oxidation reaction up above, the E value for the copper half reaction is equal to 0.34 volts. And then E for the reduction half reaction is 1.68 volts. Okay, so we can solve for the cell potential under standard conditions. Remember, this is E cathode minus E anode. And which half cell is the cathode? The reduction half reaction, right? So we'll put that first, 1.68 volts, and we'll subtract 0.34 volts. So when we calculate that, we should get 1.34 volts. Ooh, okay, so we have everything we need. So finally, we can calculate E cell under non-standard conditions. All right, so let's plug in, well actually let's remind ourselves what that equation looks like. So up above here we said that E cell under non-standard conditions is equal to E cell under standard conditions minus 0.0592 volts over N times the log of Q. All right, so let's plug in all those values. So we've got E cell under standard conditions. And then we know the number of electrons was 6. And we're going to multiply that by the logarithm of Q, which was 2.5 times 10 to the negative 7th. Okay. So this is a lot to plug into your calculator. So if you want to solve this step by step, feel free. So for instance, you could start by taking the logarithm of Q and then multiply that by 0.0592. And then divide that by 6, and then you can subtract that from 1.34. So doing things in steps can sometimes help prevent errors. All right, so once we do plug all that in, we should get 1.41 volts. All right, so is this a spontaneous process? So it is positive, so that would tell me that this is spontaneous, so that's good. All right. So the Nernst equation is really useful for situations where you're at non-standard conditions and you need to determine your new cell potential at those non-standard conditions. All right, so let's work on worksheet problem 9. A voltaic cell employs the redox reaction where 2 iron 3 plus ions react with 3 magnesium atoms to produce 2 iron atoms and 3 magnesium 2 plus ions. So we're going to calculate the cell potential at 25 degrees Celsius under each set of conditions. So we'll calculate this cell potential under standard conditions, and then in part B we're given 2 different concentrations for the ions, and then in C again we're given 2 different concentrations. So in part B the magnesium ions have a higher concentration, and in part C the iron ions have a higher concentration. So we'll see how that affects the cell potential. All right. So let's start with A. We're going to calculate the cell potential under standard conditions. So this should be pretty easy. We just have to figure out, again, what's oxidized, what's reduced. So iron 3 plus has an oxidation number of +3. Magnesium is 0. Iron is 0. And magnesium is +2. All right, so iron Is that oxidized or reduced? It is reduced. It's gaining electrons. And magnesium, is that oxidized or reduced? It's losing electrons, so it is oxidized. Okay, so now let's write out those half reactions. Okay, so we know that if something loses electrons, it's being oxidized. So how many electrons will those 3 magnesium atoms need to lose in total to become those magnesium 2+ ions? So each magnesium is losing 2 electrons, and there are 3 of them. So that's a total of 6. And then in the reduction half reaction, we have a gain of electrons. So how many electrons does each iron ion have to gain? 3. But there are 2 iron ions, so they each gain 3 for a total of 6. Okay, so it looks like it's already balanced, which is good. We know that 6 electrons are transferred, and that doesn't really matter here, to be honest, because we can just use the equation where E cell is equal to the potential of the cathode minus the potential of the anode. So that didn't really matter, but we might need that later, so we'll hold on to that information. Okay, so let's look up the potential values for each half reaction. All right, so for our magnesium half reaction, the E value is negative 2.37. And for iron, it is negative 0.036. All right, so again, just quick question. Is the oxidation half reaction at the anode or the cathode? The anode. So that must mean reduction is at the cathode. All right, so the cathode value is negative 0.036, and we're subtracting negative 2.37. All right, so that gives us a value of 2.33 volts. So E cell is positive, so this tells us that the reaction as it is right now is spontaneous. Okay, so now let's figure out E cell for a reaction where the concentrations of the ion solutions are not 1 molar, they are different. So for this one, we need to use that Nernst equation. Now, luckily, we've already calculated E cell under standard conditions. We did that in part A, so we don't have to figure that out. We also determined that the number of electrons that are transferred is 6, so we already know what N is. So we just have to solve for Q and plug it in. Okay, so looking up above, we have a solid product, and then we have aqueous ions. So remember, we're not going to include the solid in our expression for the reaction quotient. Only gases and aqueous solutions. So the only product there will be magnesium 2+, and it has a 3 in front of it, so we're going to cube that. And then in the reactants, we have aqueous ions, and then again, a solid. So we won't include the solid, but we will include the aqueous solution. And that has a 2 in front of it, so we'll square that. I made my line a little long. There we go. Okay, so now we can plug in the concentrations. So we're told that the magnesium concentration is 2.5. We cube that, and the iron concentration is 1 times 10 to the negative third. And then we're going to square that. Okay. So actually, I did not calculate this. I just plugged it into my equation. So let me calculate this real quick. So we've got 2.5 to the third divided by, let's see, 1 times 10 to the negative 3 squared. Whoa, I get a huge number. Okay. So I get 1.56 times 10 to the 7th. Okay, so now let's plug everything in to E cell here. Okay, so we need the value of E cell or standard conditions. And on the last slide, we saw that that was 2.33 volts. And we also saw that 6 electrons are transferred. And then we're going to take the log of 1.56 times 10 to the 7th. All right, so I'm going to check my answer that I got earlier. And I'm just going step by step. Okay, so 2.33 minus that. All right, so I got a value of 2.26 volts. Okay, so if we compare that to our E cell value under standard conditions, it's a little bit smaller. So would this set of conditions be more spontaneous or less spontaneous? So this will be less spontaneous because it's less positive. So these particular conditions probably aren't the best for this electrochemical cell. But if you think about it, that makes sense. We have a lot of product, right? We have a lot of magnesium ions and very few reactants. So we're probably not going to see a forward reaction occurring any longer. So it could be that we've already seen the reaction occur and it's over. Now, what if the reactant concentration is 2 and the magnesium ion concentration is smaller? So it's 1.5 times 10 to the negative 3. So what I would like you to do is calculate this on your own and determine if it's more or less spontaneous. And then additionally, I would like you to work on worksheet problem 10 on your own. And you're going to consider the reaction shown below, where chromium reacts with cadmium ions to produce chromium ions and pure cadmium. Now for this problem, you're going to first calculate the cell potential under standard conditions, the equilibrium constant, and Gibbs free energy under standard conditions. Once you've done that, you can then go on to the table below, and you'll notice that we have different sets of concentrations for cadmium and chromium ions. So what you'll do is calculate the reaction quotient, and then you'll use the Nernst equation to determine what your cell potential is under non-standard conditions, and then you'll determine what delta G is under non-standard conditions. And there are actually many different ways you can solve for all of these variables because we have a few different equations we can use. But once you have those standard condition values and your equilibrium value, it should make solving the other set of problems much easier. So this will give you a lot of good practice with these equations. Okay. So next time, we're going to discuss in a little more detail different types of batteries and cells that we use on a daily basis, or ones that we might start using in the future more often. So if you're curious about that, definitely watch the next video. If you're not that interested in electrochemistry, it's okay to skip the next video. I'm not going to test you on it too much. So, all right, I will see you potentially in the next video.